So we are going to go through this practice problem in part 2 of module 2. And this, so I'm going to go over question 1. Okay, let's see what do we have in question 1. The quality assurance department at the hospital has one of its responsibilities, verifies medical records. One of the department's employees samples medical records and checks each one of them for correctness. Historical data suggests that each medical record has a 95% chance or probability of 0.95 to be correct. So 5% chance of being wrong and 95% chance of being correct. Suppose the employee begins checking medical records at some point in time. What is the probability that 7 out of the first 10 medical records are correct? So here the experiment is checking the medical records. And can you tell me what are the outcomes of this experiment? Possible outcomes.
Being correct or being wrong.
Exactly. The experiment is correct. The medical records are correct or they are wrong. Okay. Now, there is this person who is in charge of checking the medical records, and this person is checking 10 medical records. So, so if you look at the question part A, what is the probability that 7 out of the first 10 medical records are correct? So this person, the person has checked 10 medical records. So this is equivalent of repeating the experiment 10 times. Can you tell me if the results of these experiments affect each other? For example, if the first medical record is wrong, does it affect the chance that the second medical record is right or wrong? Or the third one is right or wrong?
No.
No. So these, then one other thing I can say is that these experiments are independent. Meaning that if I know the result of one, it doesn't affect the results of the others. Okay? Now, I know what is my experiment. I know what are the possible outcomes. And I know I'm going to run the experiment 10 times. And these experiments are going to be run independent from each other. Now, I want to know what is the probability that 7 of them are correct. So with everything that we have specified so far, so the random variable x, if I want to define the random variable x to be my random variable, can you tell me what this random variable is measuring for me in this experiment setup that I explained for you? What is the definition of random variable based on what the question wants from us? That 7 out of 10 medical records are correct. So the question is asking, what is the probability that 7 out of 10 medical records are correct? So what do you think is our random variable here?
Medical records that are correct.
Number of medical records that are correct, exactly. And number of medical records that are correct out of the 10 first medical record that we checked. Okay, so that's my random variable. that out of these 10 medical records that I checked, and I know they are independent from each other, how many of them are correct? Okay, that's my random variable. Can you tell me what are possible values for my random variable? What are the possible values that this random variable can get?
Correct and wrong.
0 means no medical record is correct. What else?
1, 2, all the way to 10.
1, 2, all the way to 10. So when the random variable gets value of 10, that means all the medical records are correct. Okay. The notation that is used in the videos, this random variable x is shown by n 10. That's usually the notation that is used in the videos. So n10 shows out of these 10 experiments that we have run, it shows the number of experiments that have led to the success. And in this problem, success is defined when the medical records are correct. So that is the one that is defined as the success. If in the same experiment, if I ask you, let random variable x, if I tell you let random variable x shows number of medical records that are not correct, that are wrong, then you would consider definition of success for the medical record to be wrong. Keep that in mind. So you define what is success in your experiment. Okay, so it's not that success is always the good result. You define what is the definition of your random variable in your case that you're dealing with, and with that definition, what is defined as success. Okay, so here I'm looking at medical records that are correct. I want to know how many of the medical records that are correct. So the medical record being correct is considered as success here in my experiment. Okay. So then I can say that this random variable, what type of distribution it has, these are the possible values that this random variable can get. Do I know exactly what is the probability of each one of them? Like if I check 10 medical records, that I exactly will see 2 of them correct, or 5 of them correct, or 10 of them correct? I don't know, but I can calculate probability associated with these values. So then if I consider N10 as the number of medical reports that are correct in 10 medical records that I have checked, what is the distribution of this random variable? Binomial. And what are the 2 parameters that I need to know for the binomial to be able to answer the probabilities or the questions or anything that you ask about the binomial random variable?
The number of outcomes.
Number of experiments.
Experiments.
Okay, one is n, which we call as number of experiments. So here, what is n?
10.
Here, n is 10 in this example. What else do I need to know?
The probability of
and this is the probability of what?
success.
This is the probability of success in each experiment. Okay, and here, what is the probability of success here? Meaning that the record is correct. It happens with probability of 95%. It's given in the problem. Okay. So then, if I have these 2 parameters that I need for a binomial distribution, if I have n and if I have p, then I can answer any question related to a binomial random variable. So here, part A asks me, What is the probability that 7 out of the first 10 medical records are correct? So the probability that this random variable that I show by n10 or if or anything that you want takes value of 7. So out of all these possible values that you can get from 0 to 10, I want to know what is the probability that it gets value of 7. Okay. And based on the formula that we have for the binomial distribution, it's a combination of 7 out of 10, p to the power of 7, and then 1 minus p to the power of 10 minus 7. So that's going to be, for the combination, we always write it as 10 factorial, 7 factorial, 10 minus 7 factorial, 3 factorial, p 0.95 to the power of 7, 1 minus p, which is 0.05 to the power of 3. So we have to calculate this value to find the probability that out of these n records that we have checked, what is the chance that 7 of them are correct? I don't have the final value, but the result of this gives you that probability. Okay.
So how did you know it's binomial and it's not discrete uniform?
Okay, so the setup, what is the setup of a binomial? In the setup for the binomial, this is always the case. We have an experiment. Here was checking a medical record. The experiment has 2 outcomes. We run the experiment multiple times. The result of experiments are independent from each other. Here when I said we run the experiment multiple times, let's say n times. Let's call that n times, 10 times, 20 times, whatever. We call it n times. That's a notation. N times. The results of experiments are independent from each other. And we are interested to know number of experiments out of that 10, out of n experiments. 10 in our example, but out of the n experiments that we ran, we are interested to know number of experiments that led to success. Okay. And here, when I say they have 2 outcomes, actually, let's write it better way. Let's say each experiment leads to success or failure. Okay. We define what is success or what is failure. This is the setup of binomial random variables. If you were working on a problem where you were dealing with this type of setups, it's always a binomial random variable. For the uniform, the uniform doesn't have any specific characteristic like this. So the problem always tells you that, for example, I'm looking at the number of car accidents that may happen, I don't know, in my street today, and the number can vary between 10 to 15 accidents, and it's uniformly distributed, meaning that all of those numbers have the same chance of happening. 10 or 11 or 12 or 13 or 14 or 15, all of them have the same chance of happening. It's not that 15 has more chance of happening than 10 or so forth. All of them have the same chance of happening. So I tell you that, okay, this is what I'm looking for, and these are the possible values, number of accidents, which varies between 10 to 15, and I think all of them have the same chance of happening. So then in that scenario, yeah, uniform distribution is the one that you use. So it doesn't have a very tricky setup, uniform distribution. And here also the setup for the binomial is not tricky either. It's just that you have to know what is the setup. When you read the problem statement, you look for these things. When you read the problem statement, you search for, okay, what is the experiment here? Okay, this is the experiment. What are the outcomes that we are looking for? Okay, these are the two possible outcomes. How many times this experiment have been performed? Okay, this many times. Okay, now I'm trying to find out how many times of these n times we have achieved success. Does that answer your question?
Yes, thank you.
Okay. On average, how many of the first 40 records will be correct? Now, with everything we have talked about so far, we know this random variable has binomial distribution and so forth. Let's answer part B. On average, how many of the first 40 records will be correct? For part B, now, can you tell me what is the definition of random variable here? It's still binomial, but I want you to tell me specifically what is the definition of random variable here. I want to know on average how many of the first 40 records will be correct. So what does that tell you when I say, oh, first 40 records? I know the experiment is checking the medical record. I know the possible outcomes. Okay, so let's see which part of this, we have an experiment. So the experiment is checking the medical record. The first one is checked. These experiments leads to success or failure. Medical record is correct or not. Okay. We run the experiment n times. So how many times do you think this experiment has been run here?
40.
40. Okay, so here I'm dealing with a scenario when n is 40. N is not 10 anymore. N is 40. And the results of the experiments are independent from each other. We know that. And we are interested to know a number of experiments that have led to success. So now, if I want to use the notations in the video, then I'm looking the variable that shows number of success in these 40 experiments is going to be shown by n40. Can you tell me what are the possible values that this random variable can get?
Zero to 40.
Exactly. 0, 1, 2, all the way to 40. 40 means all 40 records are correct. 1 means only one of the 40 records are correct. 0 means none of them are correct, and so forth. Okay. So now with this setup, then I'm dealing with the new random variable, not the ones that we had in part A. So this is n40 that has binomial distribution with parameter n and p, and n here is 40 and p here is still 95% of them are correct. The chance of being correct or success is 95%. And okay, now what I'm looking for, what I'm trying to find. Okay, so tell me, what am I trying to find in part B? On average, how many of the first 40 records will be correct? What am I trying to find?
The expected value.
Exactly. Average or mean. or expected value of this random variable. So this random variable gets these possible values, 0 all the way to 40. I want to know what is the average, like most of the time, like I see around that number, things like that. So expected value of this random variable. And do you remember what is the formula for the average?
It's NP.
Exactly. If I have a random variable that has a binomial distribution with parameter n and p, then average is always np. And what is variance?
It's NP times 1 minus P.
Exactly. That's cute. Well, let me. Exactly. Variance is np 1 minus p. Okay. So now when the question says on average, how many of the first 40 records will be correct, then that just needs the average of this random variable that we defined here. Okay. And that's going to be NP. I know N is 40 and P is 0.95. So whatever that number is, that's your average number of records that will be correct in these 40 records that we have searched. Okay. If you needed to calculate the variance of this variable, that would be NP 1 minus P. 40 multiplied by P multiplied by 1 minus P, which is 1 minus 0.95, which is 5. So that would be your variance. And your standard deviation would be a square root of variance. Okay. Any question? Okay. Let's go to question 2. Just make sure we are recording. Yeah. Okay. Question 2. In a clinical study, volunteers are tested for a gene that has been found to increase the risk of a disease. The probability that a person carries the gene is 0.1. There's 10% chance that each person carries that gene. If a total of 60 volunteers are tested in the clinical study, what is the probability that 12 of them carry the gene? Okay. I want you guys go through these steps that we just talked about and help me to figure out what type of variable we are dealing with here. Okay, so there is this clinical study. They check people to see if they have a gene. Each person has 10% chance of having the gene. If a total of 60 volunteers are tested, what is the probability that 12 of them carry the gene? Okay, someone tell me, are we dealing with an experiment here? What is that experiment? You hear me, guys?
It's people being tested. That's the experiment.
Exactly. Testing each person for the gene is the experiment. That is the experiment. Does this experiment lead to success or failure or some outcomes?
Yes.
Yes.
You have the gene or you don't.
Exactly. When a person has the gene, that's one outcome. When the person does not have a gene, that's another outcome. Are we going to, step 3, are we going to run this experiment multiple times? And how many times is that, if that answer is yes?
Yes, 60 times.
You said 60?
Yes.
Okay, yeah. So when the part A says if a total of 60 volunteers are tested, that means we have run this experiment 60 times. We have run it once, check person 1, and then check person 2, and then check person 3, all the way to person 60. So that, and then, oops, what? Then that means, yeah, we have run this experiment multiple times. How many times? 60 times. Can we say the results of these experiments are independent from each other, meaning that if you find the first person has a gene, that has nothing to do with the second person having the gene or not? Are these experiments independent from each other?
According to the question, yes.
Yeah. Yeah, and also, as I said, these are different people, right? So the fact that the first person has the gene or not has nothing to do with the result of the second person having the gene or not. It's just just checking these people's and the results of each person. They are independent from each other. So these experiments are independent from each other. And okay, so the experiments are independent from each other. So this condition is met as well. And are we, okay, no, not the last part. Are we interested to know the number of experiments out of these n experiments that we have run that lead to success? Are we looking for something like that? How many experiments out of these 60 experiments that we ran led to success? Are we interested in anything like that?
Yes.
Can you tell me where did you get that?
It's part A, that the 12 people.
Okay, in a total of 60 volunteers, what is the probability that 12 of them carry the gene? Which is exactly, we are interested in number of success, which in this case, I'm looking for the number of success to be 12. Out of these n experiments, out of these 60 people I have checked that have the gene, which is the success here in my experiment. Okay. So then, as a result, I am looking at the binomial random variable. I'm going to show it as n, capital N, lowercase n, like the notation in the video, that's n60. And this random variable has binomial distribution. The two parameters that I want are n and p. Here, n, the total number of experiments that I have run is 60, and p, the chance of success in each experiment is what?
0.1.
0.1. So remember here, I said when we run the experiment, it can lead to success or failure. Okay. And then here at the end, we need number of people, number of experiments that have led to success, right? Here you see. You define what is success for you. Here, in this example, what is the definition of success?
Having the gene.
Exactly. Here, having the gene is success for you. And that probability, as the problem statement has given to you, is 0.1. If I tell you, if I change the question and then I tell you, out of these 60 experiments or 60 people, what is the probability that 20 of them do not have the gene? Okay. If I'm asking you that questions, then you are looking at number of the experiment you have run is 60 times, and still it has binomial distribution, and still the number of experiment is 60. You have tested 60 people. However, the definition of success in this question is different from the previous one. Success here is defined when a person does not have the gene. Okay? And in this problem, if everything that is given you is the one that you have in the question, then the chance of not having the gene is 0.9. Okay? Then if I want to again use the formula, do all the calculations, then the P that I'm going to use is going to be 0.9. That's the P. If I ask you, what is the average number of people who do not have the gene? When you look at NP, then the P that you're going to put here is 0.9, because I'm looking at average number of people that do not have the gene. So not having the gene is success in this part, in this exam. Yeah. Oops. Yeah, so not having the gene then becomes success in this part. Okay, so my point is that, yes, we run the experiment. Every experiment leads to success or failure. And at the end, I want to know number of experiments that have led to success. Depending on what the question wants from you, you define what is success in your case and what is failure, and just to stick to it. It doesn't matter if they match to the real world definition of success, but you define as the outcome of the experiments, what are the outcomes, what is considered as success, what is considered as failure in your problem state. Okay. So now, just make sure you do not confuse this part. This was the example I gave to you. So now we are going to use the same setup that I have on the top. So I have this random variable that has binomial distribution. N is 60, and P, the chance of success, which is not having the gene, is 0.1. Tell me, what does the question want? If a total of 60 volunteers are tested in the clinic, what is the probability that 12 of them carry the gene? So then that's probability of N60 equals to 12. What are the possible values that this random variable can get? Can you tell me? All possible values that this random variable N60 can get for?
0, 1, all to 60.
Exactly, 0, 1, all the way to 60. These are possible values. Now I want to know the probability that this variable gets value of 12. 12 of those 60 volunteers have the gene. So 12 out of the 60, P 0.1 to the power of 12, and 1 minus 0.1, which is 0.9, to the power of 48. Whatever that number is going to be. Okay. And then part B, how many person that carry the gene do you expect to be detected if 40 volunteers are tested? Okay, so read the question, read part B one more time. How many persons that carry the gene do you expected value to be detected if 40 volunteers are tested? If I go up to here, the setup of the random variable, binomial random variable definition, can you tell me which part has changed and which part has not changed? I still have an experiment. I'm good with the first part. I'm testing people for a gene. The result of the experiment is still success, has success or failure. Okay, the experiment has a couple of options. How about the next part? How about
N
this?
equals 40 now?
Exactly. The question tells you that if 40 volunteers are tested, so now then N is not 60 anymore, N is 40. And yeah, and then the result of the experiments are independent from each other. This one is good. And I'm interested to know number of success in this for the experiments. So yeah, so then the total number of experiment has changed. So if I want to come here in part B, I'm looking at N40. Total number of experiment is 40, which has a binomial distribution. N is 40 here. P, the chance of success or having the gene is still the same, 0.1. And what am I looking for here? Can you tell me what do I need to calculate?
Expected value.
Exactly, average or mean or expected value of this random variable. And that's NP 40 multiplied by 0.1. Okay. Any questions so far? Let me see. I'm trying to find a problem since we don't have much. Some uniform distribution thing to solve for you guys. There is, yeah, all of these are binomials because just a binomial is a little harder than. If I want to give you an example of a uniform, uniform random variable. So let's look at the ones that we just talked about. So I'm looking at I'm let my random variable x to be number of accidents, let's say, in part of the highway. In each week. Okay, that's the one that I'm going to look at. And x varies between 10 to 16, let's say, accidents. And I also, all these possible values have the same chance of happening. Okay, in that scenario, you can say X has uniform distribution. And what is the minimum? Or A, lower bound?
10.
10. What is the maximum?
16.
Or B, that's 16. So then if I tell you on average how many accidents we get, so average number of accidents per week in this highway, that's A plus B divided by 2, right? 10 plus 16 divided by 2 That's going to be 13. If I ask you what is the variance or standard deviation, just use the formula. If I ask you what is the probability of observing what is the probability of observing exactly 12 accidents? What is that probability? Can you tell me, with this definition I gave you, X has uniform distribution, minimum is 10, maximum is 16. Can you tell me what are possible values?
1 over b minus a plus 1.
No, possible values that this random variable can get. 10,
all the way to 16.
11, 12, all the way to 16, right? These are all possible values that this random variable can get. Even before you know the formula or to use the formula, can you tell me what is the probability that each one of them happens? I observed 12 accidents, or 11 accidents, or 10 accidents.
1 out of
1
7.
over 7.
1 out of 7. So 10 to 16, there are 17 possible outcomes. All of them have the same chance of happening. So the probability of each one of them happening is 1 out of 7. But so the probability that exactly 12 accidents is observed is 1 out of 7. But I can also calculate that using the formula. That's probability of this random variable getting the value of 12. So the probability mass function, which is 1 over b minus a plus 1, right? 16 minus 10, 6 plus 1, that's 1 over 7. Okay, so that's how the formula is used. That's how intuitively we calculated that value. Tell me, what is this? What is the probability that at most 12 accidents is observed in a week?
Three out of 7.
Exactly. When I say at most 12, that means the maximum is 12, but 10 accident is also accepted, 11 accident is accepted, 12 accidents is accepted, but 13, 14, 15, 16, they are not accepted. They're not in this scenario. At most 12, that means X can be 10 or 11 or 12. Each one of them is 1 over 7. So that's 3 over 7. So that's at most 7. Okay, at most. What if I tell you, then obviously when I tell you probability of at least, for example, 14. Let me just change it so we don't get necessarily similar numbers. At least 15 accidents observed in a week. What is this probability that I observe at least 15 accidents in a week? At least means what? What are the possible values here? When I say at least 15, what are the things?
So it's this 15 and 16.
15?
Oh, yeah.
Exactly. And 16. At least 15. Okay, 16 is okay too. Each one of them is 1 over 7. So that's 2 over 7. Okay? Pay attention to these keywords. at least, at most, exactly. These are the keywords that you can also use in any random variable. For the binomial, also can tell you this. What is the probability that, for example, for the binomial examples that we just had here, for the experimenting on 60 genes, for example, what is the probability that we find at most 12 people that have the gene, as opposed to exactly 12 people that have the gene? If I ask you what is the probability that at most 12 people have the gene, then you have to calculate the probability of n6 equals to 0, 1, 2, 3, all the way to 12 and add all of them together. Okay. Any questions so far, guys? Okay. Our time is up. Make sure to go through the other questions. So as I said, they are just good practice problem help you to learn more about the binomial and uniform random variables. If there's any question, feel free to ask me. Let me just, for question 3, clarify something so that you don't get confused with the structure of the problem here. Consider the experiment, whatever reactions in the table below. These reactions are performed, and we record the temperature in each one of them reactions. 48 of these reactions have 226 for the temperature, 60 of them have 271, 92 of them have 274 reactions. And then a total of 20 independent reactions are to be conducted. What is the probability that exactly 12 of them results in a final temperature less than 272? Okay, actually, let's look at this one. It gives you a good sense of everything we talked about so far. Let's go to the setups of the binomial. Okay, help me here, guys. What is the experiment that we are talking about here?
The different temperatures on, can't recall, sorry.
No.
The 20 independent.
No. I want you to tell me what is just the experiment. Like, for example, testing people for a gene is the experiment. What was the question one? The checking the medical record is the experiment for question 1. Tell me what is the experiment here? But just one sentence. What is the experiment? Definition of the experiment here.
Checking the final temperature of the
Performing the reaction, I would say, and looking at the temperature. Okay. Performing the reaction would be the experiment here. The temperature is the outcome, like the people having the gene or not, or the medical record being correct or not. Those are outcomes. But the experiment itself is performing the reaction. Okay. And okay, so that's my experiment. Does this experiment lead to success or failure? And if you want to know that, let's look at the question. For now, just focus on part A. Part A, it says, what is the probability that exactly 12 reactions resulted in the final temperature less than 272? So what do you think is called success and what is called failure here?
less than 272 and over 272?
Exactly. So then I define the success here to be, let me erase this. I define the success to be temperature less than 272. That's success in this setup. Okay. And then the next thing, we run the experiment multiple times. And how many times we run the experiment here?
20.
20. You see below the table, it says a total of 20 independent reactions are to be conducted. Okay, so then n here is 20. We run these reactions. Are the results of the experiments independent from each other? Yeah, it says even in the problem statement, we run n 20 independent reactions, so they are independent from each other. And then the question that has been asked from you, are we interested to know number of experiments that have led to success out of this n experiment that we ran? Are we interested in anything like that?
Yeah, we want to know if 12 of them are going to be less.
Exactly. We want to know that out of these 20 reactions, what is the chance that 12 of them lead to success, which here is the temperature being less than 272. Okay, so this has everything that is the setup of a binomial random variable. So then here, this is what I have. I have a random variable, I call it n20, because the lowercase n is 20. We run the experiment 20 times. And this has binomial distribution n, lowercase n, which is total number of times that I run the experiment is 20. And then I also need p, which is the chance of success. And here, success means temperature less than 272. Do you have the chance of success here? Is it given to you in the problem right away, or do you need to do some calculations to find it?
To do some calculation.
What do you need to do? So basically this table is some historical data that you have from the past. This is all I have to calculate whatever I need in this problem. So now, given this historical data, tell me how I can find P, the chance of success in this setup. So the success is temperature less than 272, right? So if I wanna here find P, the chance of success in this setup, which is number of temperatures, the number of experiments when or number of reactions when the temperature is less than 272. Can you tell me how many of the reactions have led to temperature less than 272?
108.
48 plus 60 out of how many?
200.
Exactly. So this number will give me the chance of success that I can use in this setup and then find the probability or anything I need. Okay. So this actually was a good example in the sense that you guys see that when you run these experiments, you actually get three outcomes. The temperature can be either 226, 271, 274. That's fine. You can get maybe 1,000 outcome when you run these reactions. But in the problem statement, you have to see what is success and what is failure for you. Success means when the result of the experiment is less than 272. Okay, try to find that. Everything else is considered as failure. So I don't care if my experiments have, I don't know, 20 outcomes, like my experiments have 100 outcomes of 100 type of temperatures or whatever. I know what is success when the temperature is less than 272, that's considered as success. And I just try to find that. And as long as I can find that, that's all I care about. Everything else in this setup is considered as failure, will be in the failure category. I don't care about them. They are failure. So that's the setup of this problem. As long as you know what is the experiment that you are not running, how many times you are running the experiments, making sure these experiments are independent from each other. What is success or what is failure in this experiment? And what is the chance of success? You have everything that is the setup of a binomial random variable. The rest is easy and just putting the numbers in the formula and nothing tricky about it. But just make sure to read the problem carefully, make sure you can figure out these pieces so you correctly identify if a random variable is binomial or not, and then you're good to go.